6.2 Equilibrium constants. At the end of this lesson, you should be able to define homogeneous and heterogeneous equilibria and to write expressions for equilibrium constants in terms of concentration Kc and partial pressure Kp for homogeneous and heterogeneous systems. Homogeneous equilibrium is the reactions in which all reactants and products are in the same phase. As you can see in the following equations, all the reactants and products are in the same phase. Heterogeneous equilibrium is the reaction in which product and reactants are not in the same phase. For example, in this reversible reaction equation, the reactants and the products has two different phases, which are liquid and gas. So, this reaction also can be defined as the reaction in which the reacting substances are in two or more phases. Writing Kc expressions. Let's consider a general reversible reaction of A plus B produce C plus D. The capital letter A, B, C, D represent the reactant and the product, while the small letter A, B, C, D are stoichiometric coefficients, means A mole of A, B mole of B. So, we can write the equilibrium constants expression by multiplying of all the products C and D and dividing by the product of the equilibrium concentration of all the reactants A and B with the concentration of each substance raised to the power of its coefficient in the balanced chemical equation. So the small letter C, D are the power of product. Small letter A, B are the power or the coefficient of the reactants. Subscript C in Kc here is the concentrations of the reacting species. The square brackets here indicate the molar concentration of the substance within the bracket. Thus, if we have the equilibrium concentration for the decomposition of N2O4 to NO2, the equilibrium constants expression is Kc square bracket to indicate the molar concentration, NO2 are the concentration of product to the power of 2. 2 is the coefficient of NO2. 2 mole of NO2, so 2 becomes power. Divide by the concentration of N2O4. N2O4 has 1 mole. So the coefficient of N2O4 is 1. But 1 is not written in the equilibrium constants expression. The second example, we have CH3COH 1 mole produce 1 mole of CH3COO minus plus 1 mole of H plus. So, the Kc can be written as square bracket CH3COO minus to the power of 1 multiply with concentration of H plus to the power of 1 divided by the concentration of CH3COOH to the power of 1. Again, 1 is not written in the concentration expression. So the unit of concentration is molar, or it also can be written as capital M or mole per liter. Consider again the equilibrium equation for a general reaction of A plus B produce C plus D. So the Kc is the concentration of product divided by the concentration of reactants. But if we write the chemical equation in the reverse direction, the new equilibrium constants expression is known as Kc prime. So the concentration products divided by the concentration of reactant. And the value of Kc prime is 1 over Kc. Writing Kp expressions. Because gas pressure are easily measured, equilibrium equation for gas phase reactions are often written using partial pressure rather than molar concentration, where P is the equilibrium partial pressure of the gas. It is the partial pressure of the gas. For example, in the decomposition of 1 mole of N2O4 to 2 mole of NO2, it can be written as Kp equal to the normal bracket PNO2 means the partial pressure of NO2, the product, to the power of 2. 2 is the coefficient of NO2, 2 mole NO2. Mole will become the power. Divide by the normal bracket of PNO24. PNO24 is the partial pressure of the concentration. Partial pressure of N2O4, Because of we have 1 mole of N2O4, so the power is 1. But 1 is not written in the equilibrium constant expression. The second example we have for 1 mole of N2 plus 3 mole of H2 produce 2 mole of NH3. So Kp can be written as normal bracket PNH3, partial pressure of NH3, to the power of 2. 2 is the coefficient of NH3, divide by normal bracket Pn2, partial pressure of N2, to the power of 1 because N2 has 1 mole. 1 is the coefficient of N2. Multiply with normal bracket pH2, partial pressure of H2, to the power of 3. 3 is the coefficient of H2. Unit of pressure can be any normal pressure unit, but commonly in ATM. Equilibrium constants expression, Kc or Kp, also called equilibrium law expression. Writing Kc and Kp expressions. We take for example the thermal decomposition of solid calcium carbonate, a reaction used in manufacturing cement. When the reaction is carried out in a closed container, three phases are present at equilibrium: solid calcium carbonate, solid calcium oxide, and gaseous carbon dioxide. If we were to write the usual equilibrium equation for the reaction, including all the reactants and products, we would have Kc equal to the concentration of CaO and concentration of CO2 divided by the concentration of CaCO3. But because both CaO and CaCO3 are pure solid, their molar concentration are constant. So, we can rewrite this equation as Kc, the concentration of CO2, and Kp as partial pressure of CO2. So, as a conclusion, the concentration of pure solids, pure liquids, and solvent do not appear in the equilibrium constant expression. Why? Because the concentration of pure solid and pure liquids are constant. Why pure solids and pure liquid are constant? A pure solid always has the same concentration at a given temperature, means the same number of moles per liter of the solid. It can be calculated from their densities and molar mass, just as it has same density at any given temperature. In general, the concentration of any pure solid is independent of its amount, because its concentration is the ratio of its amount in moles to its volume in liter. If, for example, you double the amount of calcium carbonate, you also double its volume, but the ratio of the two, mean the concentration, remains constant. Same reason applies to pure liquid. As a conclusion, in this reaction, the partial pressure of carbon dioxide did not depend on the amount of calcium carbonate or calcium oxide. Exercises: define homogeneous and heterogeneous equilibria and write Kc and Kp for the following reactions. I hope you can answer all these questions in order to achieve learning outcomes in this subtopic.